Okay, hello everybody to this week's ISGC seminar talk. Today's speaker is Burin Gumjudpai. He received his PhD in 2003 from the University of Portsmouth, and since 2020 he is a professor for theoretical physics at Mahidol University, and he is in addition also adjunct professor at Nariswan University. Thank you, Burin, for agreeing to give this talk. The stage is yours.
Hello, everyone. This is Burin Gumjudpai from Mahidol University in Thailand. So I would like to talk about cosmology dynamics of the holographic dark energy with non-minimal coupled scalar field. And this is the work that I finished with my PhD student, Montep Tita. This is from NA, so NAS Center for Theoretical Physics and Natural Philosophy of Mahidol University in Thailand. This work based on arXiv 2507.205.273. Okay, let me introduce you to the non-minimal coupling. So as all we know that the late time universe acceleration with the equation state should be about -1. We should really agree well with the cosmological constant up to at least 1 sigma. And you need the grateful exit to have this a level of suitable prediction of the CMB anisotropy and also the origin structure from the inflation consistent with the observed anisotropy of the CMB data. So the major option to explain this is to use the modified method, which is dark energies ideas, or you can modify the gravitational sectors, which is a very geometrical part in the Einstein field equation. And then if you want to mix this modification together, so you have a lot of ideas. For example, Jordan-Brown-Dickey scalar tensor models. And one of the models here that we consider is non-minimal coupling model. From now we call NMC. And this is the coupling between the scalar field to the Ricci scalar. And most of the models in this category allow present acceleration and also allow early acceleration in the early universe, the inflation. So this term of the non-minimal coupling emerged from also the renormalizing of the quantum field theory in curved space-time in supersymmetry, superstring, and also many of the low energy effective theory of the quantum gravity. So this form actually fall into a subclass of the Horndeski theory with the Jordan frame action. So we write this action as a low energy effective theory, and it's a subclass of the classical Horndeski theory in the Jordan frame action. So you can see that the first term is only the Ricci scalar, and you have a coupling here between the field. The coupling constant is C here, and you have a kinetic term, potential term, and matter term, plus the cosmological constant term here. And if you do factorization, that's gymnastic a little bit. So you will write down G effective in this term, where G effective is actually the standard gravitational constant G divided by this one. And the second term actually the coupling between the square of the scalar field and the coupling constant times the square of scalar field. Okay. So in G effective, it encode the non-minimal coupling in here already. So whenever you have G effective, this is a function of the scalar field and also have an effect of NMC here. So in here, we also consider the scalar field in this form, where we consider the case of P is 2, and where P is 2 is a quadratic potential. And in the standard case, based on the work and my colleague Shinji Tsuchikawa have done long ago. Actually, most of the result of it is his contribution, not mine. We found that actually the C should be greater than -7 times 10 to the -3. This is a constraint. So that means it's very, very slightly minus very slightly minus in 1 in 1,000. So this motivation and work actually based on this reference on the right. Okay, so now we talk about the benefit of having G effective. Why it's good about G effective? Because if you have G effective, you will have a locally scale-invariant extension of GR, and this is based on Y geometry. Secondly, you can see that the instability that caused from the NMC with the G effective can cause the cosmological constant damping. That means, so at the end, the behavior at late time will act similar to the cosmological constant. And then you can find that many of the still viable cosmological models are developed from the NMC theory right now. So you can find this from the work by Ford, Littis, Smolin, and Gong and Yi. So if we consider cosmological perturbation for this NMC model, the constraint that we have been working is C is greater than -7 times to 10 to the -3. And for P is equal to 4, the model is disfavored. So then if you use this model, the non-minimal coupling case, so we can rescue that model for P equal to 4. But the constraint is different. But this is not our interest here because we are really interested in terms of when P is 2, it's quadratic potential. Okay, let's see if we add the holographic effect into this NMC theory. What is the difference? What is the prediction? Right. So the aim of this talk is just to have a model or the dynamical models that you can explain what is the early universe, which is give you whatever stiff fluid effective dynamical behavior. And then if we ignore the radiation dominated epoch, we go to dust dominated epoch, and at the end we go to dark energy dominated epoch. Crudely, so it is now also, you can see that this MNC model is like a sort of grandson of the quantum gravity for example, string theory. So it will be very difficult to consider very generalized case. And then we want to have very simple model. So we just consider an MC model. But actually this term NMC just fall into one term of the Lagrangian in the Horndeski Lagrangian. The other term is called non-minimal derivative coupling. It's also very interesting. But at the end, our previous work, we just found that this is completely ruled out if you try to use NMC DC model for the inflation. So that's why we think that this NMC model is viable than NMDC model. Okay. So not to get you lost, NMC model is actually the coupling between the scalar field itself to the Dicey scalar, not the derivative term of the scalar field. Okay, let's talk about the holographic principle. Okay, I'm not the expert on this quantum gravity, so I might say something stupid. So forgive me if I do that. So HDE stands for holographic dark energies. Then this one is good because it can explain that the small observed value of the present day quantum energy. Why is it so small? Why it's not so big? Because you have that problem, right? That you have a prediction from quantum field theory that's very large, and then the observational Hubble parameters that predict that you should have very low low energy density for the cosmological constant. So in 93, TUF just proposed this holographic principle, and basically it said information about a volume surface encoded by the boundary. Okay, in string theory, entropy of the volume is proportional to the area of the surface boundary. That means whatever information in the box you can also have another theory on the volume, on the surface that is equivalent to the theory on the volume. So when you say in the volume on the box, you will have one extra dimension. That means suppose the box is three-dimensional, the surface is going to be two-dimensional. That you have a dual theory that you can explain this. Okay, and after that, in Bekenstein-Hawking entropy, this one has been proposed to say that, okay, information of a three-dimensional black hole, all this information of black hole encoded on the surface, the two-dimensional event horizon. So that means if you take this Bekenstein-Hawking relation, you will have Bekenstein-Hawking entropy. Let's say that, okay, the surface of the black hole, which is the dimension of L squared, is actually proportional to the entropy of the black holes, where now L is a Schwarzschild surface. And further, so a matter volume with entropy, if you have a volume and the matter inside the volume exceeds the limit of this SBH, that means information exceeds the upper bound, then the volume turns to be the black hole. That means this boundary is the maximum information that the bulk volume can take. At the same time, the other group of the people is consider a field theoretical approach. If you have a box the size of L and you have a UV cutoff with lambda, and you try to sum all the energy modes in the quantum field theory. So you can, if you sum all the modes just to find the value of the energy density inside, which is the sum of the vacuum energy mode, you need to have a cutoff, like that UV cutoff. And this predict that the entropy of the volume should be this relation. And you can see that you have this L cube here, this is L square here, and lambda is here as a UV cutoff. So you can see that the field theoretical delight is hence bounded by Bekenstein. That means you can't have this one larger than this one. Otherwise, this volume becomes a black hole. Okay. Then, and Trupp and Susskind just found that the derivation of the quantum field theoretical derived entropy is large than it should be, because they are the sum of overcounting degree of freedoms. So in this point of view, it's very technical, and I'm not quantum field theorist. So from the literature, I think it's a very, very nice work. And you can find it in the literature here. I have give you on the right-hand side. All right. And then in 1999, there are three people, Cohen, Kaplan, and Nielsen, proposed a restrictive limit more restrictive limit than the Bekenstein limit. I mean, Bekenstein limit is tight already. If you have that exceed the limit, you have a black hole rather than just a bulk volume. But then for this K, C, and bound, Cohen, Kaplan, Nielsen just propose that actually you can remove square here and give it just one, and just put this L to be L3. Sorry, remove from 2 here, you have 1 here, and then you change 3 to 4 here, and you can have this secant bound. And from the dimensional analysis, you can see that the secant bound give you the energy density of whatever vacuum energy is a volume in this form, that is equal to the length scale divided by 2g. You can also rewrite this in terms of Planck mass. And this means that if you sum over the serial point one loop collection of the energy density in the effective field theory saturated by this bound, you can write down this one. So most of the cosmologists who are not quantum field theorists just take this result as a grant and use it. And I'm one of them. So it says that the energy density of the vacuum energies is 3 times some constant and divided by S pi g, and this is a cutoff length scale. So this is a low energy cutoff length scale. So at the beginning, Well, they ask what is a reasonable cutoff length scale. So they come up with, okay, let's try. If the universe is a bulk volume, it's not a black hole, but then the information of the universe should be on the horizon of the universe. Because in black hole, you have a black hole, a mass in there, and the information is on the event horizon of the black hole. But now you consider in the cosmic case. So universe should have at least the horizon. And then you have a sphere, surface sphere, over this bulk universe. So they propose that, okay, let's use the Hubble length scale. And then, so this one will give you a trouble at the end. If you use the Hubble length scale, you can find that this energy density is just approximately equal to the dark energy density that required from the observation nowadays. And then that's why this idea, when applied to Hubble length scale, we call this one holographic dark energies called HDE. Okay, but the problem come along when you use Hubble horizon with this length scale. It gives us equational state parameters. We expect it to be dark energy, but then it gives the bill 0. And that is a very great work by S. Chu in 2004. But then the caution for me is that actually to get the dust-dominated universe for this length scale for the holographic dark energy, you have already assumed a flat universe, and also there's nothing else in the universe. There's only HDE domination. That means if you have the other matter field like scalar field or dust, this is about to change, and it's not really a detector behavior. Okay, so some other groups just use the particle horizon, and then it doesn't give you a very expected result because it gives deceleration, because you have the bill of this energy density greater than -1/3. And then if you use future particle horizon, give you acceleration, yes, but then you have a causality problem. So this is a lot of review by, for those who are interested, I just recommend you to see. Can you see this? Because it seems that this black bar is blocked from my view. Let me do this. Okay. All right. This is better. Yeah. Okay. And then another review work by Longjun Kai as well. And Miao Li as well. Okay. Miao Li should be Miao Li. Okay. So for the secant valve, if we try to write down the cut of the secant valve, Miao Li have this review paper, and in his review paper he do dimensional analysis for law. So in that review paper, he said that the first term for the dimensional analysis, you can have this term, second term is this one, third term is this one, and so on, just to make each term has the dimension of inverse length squared to the fourth. And then if you compare this with our case, you can see that the first term is actually the cosmological constant, and the second term with the same dimension is actually the holographic dark energy models. So that is quite nice, but I don't expect it to go to the third term because there's no mass term in here explicitly. Okay, so let me wrap up for this one. Now when you say we have holographic backup energies, now whatever we are okay with right now is this term. And then what they usually change from this one because they modify the form of the entropy, not really the classical entropy, but in quantum entropy. So then this term is going to be about to change if you change how we define entropy. And then also there are another option that you change the length scale type, so you have another kinematics and dynamics if you change. Okay, and then in this there are lots of literature in this area. If this is only the people who are using holographic dark energy cutoff with the NMC and also NMDC, non-minimal derivative coupling. So including our group here in Thailand. Right. Okay. So what cutoff energy, what cutoff length scale that we want to use in this model is the apparent horizon cutoff. We have a good reason to use apparent horizon cutoff because the apparent horizon cutoff, when you put it in the situation that universe is under accelerating, so the accelerating space-time is actually the same mathematics with the trapped null surface. And that trapped null surface is actually the black hole event horizon. That's why if you use event apparent horizon, so it be the natural choice for holographic cutoff. Because now the universe is not like decelerating expansion, but then accelerating expansion. You have trapped null surface, that means you have a horizon that then light signal can never reach, can never approach. It just forever. Okay, so this form of the apparent horizon is written like this. When k is zero, the apparent horizon is actually the Hubble length scale, the same. So now we consider when k is not zero. That means we include the curve case as well, curve space case as well. Okay, and there was a very nice work, very classic one by Kai and Kim in 2005, and this has a link between the first law of thermodynamics at the horizon. And if you put down the first law of thermodynamics at the horizon, you can automatically derive the Friedmann equation. And that's a really good link because the Friedmann equation comes from the thermodynamics first law. And then if you have thermodynamics, you have to define temperature and entropy. And in analogous to Hawking entropy. So this is called Kai-Kim entropy. But I'm not going to talk about Kai-Kim entropy right now. Our model based on apparent horizon. So we advocate this paper. All right. Now we are having NMC and the HDE right now. So let's look at the action again. This is the action in the Jordan frame. And if you do a lot of steps, you will come up with this field equation. Okay. This is the Einstein field equation with something complicated on the right-hand side. And also on the left-hand side is also a little bit complicated because you have NMC coupling here. Right. Now the matter contained in this theory is the NMC scalar field. It's the MMC scalar field is this one. And the dust matter is this part in the Lagrangian. And the holographic vacuum energy in this one. Okay, and then since you have NMC scalar field, you have also this typical scalar field, the canonical scalar field, the potential term. So when I say NMC, I mean all this scalar field. And then this one scalar field, one single entity object scalar field, have this part that coupling to the Dicke scale. Some of the models, some of the papers consider this part as a potential by just take this term 0, because actually if you have a phi square potential, this is very similar to the potential term because this is also phi square, right? So I don't know which one is right or wrong because there's no observational constraint to rule out yet. Then it is to use in the iterations, but we keep both. Right. So you have a field equation. Okay. And then after we have field equation, this is have been known already by many people. And it's not the result of a group of my work because it's MMC theory. So you have equation motion and also the Lesha-Hurley equation here, and then the Klein-Gordon equation. You can see that the Klein-Gordon equation doesn't have any vacuum energy effect, but the vacuum energy effect just appear in the Friedmann equation and also the Legendre equation or the acceleration equation. Okay, now we try to do a dynamics of this system. But then before we try to do the dynamic of the system, we have to really need to tell what is this low lambda. Okay, so we go back and use this KC and bound and define low lambda. The KC and bound saying that this should be written as 3c squared 8 pi g L squared. But then we are encouraged to use G effective. Okay, and L is actually the apparent horizon, and L squared is actually L squared down here is actually this term, this is a nominator from the denominator. Okay, there. So G effective, why we use G effective? Because we are now consider the model that if you take all the NMC effect at the Lagrangian level, you can factorize it out. And then in the Lagrangian, you will see the NMC effect as a G effective only. You don't see the NMC effect in the other term in the Lagrangian. That look very natural because you do it from the beginning. So then it means physically, it means you have a universe, FRRW universe, and you have scalar field, canonical scalar field, matter field, and vacuum energy. But right now, the gravitational constant can evolve. It becomes effective gravitational constant. This is how we interpret this. Okay. Right. And then we go to some mesh work because we are forming the dynamical system. I'm not going to talk about this in detail because the audience says what we had it. All right. So we have a lot of dimensionless variable, but actually 4 of them are independent. Not all of them, but we need to write down because otherwise we can't really make it in order. We can't even write a equation. That means we put all the equation and plus some constraint equation that related these 7 parameters together. Okay, so X is actually the kinetic term, but then the kinetic term also have G effective here. That means you have NMC here already, NMC here, NMC here, and all terms have NMC here because all of them have G effective except the curvature term. Okay, the curvature doesn't have explicit non-minimal coupling effect, but the other term have explicit non-minimal coupling effect. Why is this? Because the minimal coupling effect C is here. Okay, let's see how we define the point of beginning. Okay, there. You see, you have non-minimal coupling effect in the G effective and the scalar field. So G is a function of scalar field, G effective. Okay, let's come back to the slide. Okay, so now, as you know that the matter contains now NMC scalar field dust and vacuum energies. So the Friedman equation can be written in terms of this parameter in this form, but also you have the other constraint. This one is another constraint among this. That means you have 1 degree of freedom less. And this one and this one. So from 7 variables, you have -3 constraint. You have only 4 independent dimensionless variables. Why 4 of this is important? Because you can't arrange mathematics in order to be free. You have to write down the simplest one is this, but then you add the constraint later. That's it, what we can, it's possible for us to do. Or maybe we are not that clever enough. Right. Okay, hence then you define the intensity of scalar field in this form. Although we seem that you have a scalar field more in the effective G, but then you have this term. It actually, you can't say this is a damping term or not a damping term because of it, you have to talk about this damping term in the Craig-Gordon, right? But you have this phi dot here, and that seems that the phi dot also coupling into the field, and also coupling to this Dichy curvature expansion as well. And that could give you both the friction and the other thing, okay, in the Klein-Bardon equation. And the pressure is defined this, and okay, you will have this feedable dot form Klein-Bardon field, and that will be very complicated. Okay, so then the bill is defined this with these parameters, and we use the continuity equation for the vacuum energies. But now you have to understand that now the vacuum energy is not actually the constant, because it can evolve, because it's now the holographic vacuum energies. Okay, and then you add it together, you have this one, too detailed. And you have autonomous system. But the autonomous system, we have only four, because now we have four independent variables. And then epsilon here, it means this one. Okay, this is a standard epsilon. And dash is a derivative with respect to the E folding number. Okay, then you have fixed point. You don't want to look at it in because it's my work, but then also very difficult to remember which is which, quite complicated. You have 9 fixed point, and each fixed point come into this value, which look like a 7-dimensional value, but then it's only 4 independent. Okay, let's interpret this 9 fixed point. After we have fixed point, we got to find the eigenvalue for the fixed point, and we find that the fixed point 1 is shadow. Fixed point 2 is shadow or unstable up to the condition that we have this. And shadow unstable up to each condition that we put it here. We just try to find all the possibility that we can find solution. And then at the end, we find that the equation state for each fixed point is written in this form. So fixed point 1, the bill effective is indeterminate. Fixed point 2 is 1/3. And fixed point 3 is minus 1/3, sorry. And because it's minus 1/3, it's at the boundary of this acceleration and deceleration. So it's not really realistic, because right now we don't have this universe with minus 1/3, right? And fixed point 4 is good because it gives you cosmological constant. 5 is on this conditional, and B is very long, this term. And the B is a constant. It depends on the effect of the NMC, sorry, the holographic effect and the NMC effect here. Okay, so B is -1, and then you add up this effect. When you have GR case, you can just say that, okay, GR case, if you have vacuum energies, you have C is 1. But if you don't have vacuum energy, you just put C 0. And then for the GR case, without non-minimal coupling, you can just put C here is 0. Okay. Okay. So with this 9 fixed point, if I talk about this in the seminar here, it will be very boring, because if you have to look at thoroughly, it's a lot of mathematics at the same time. I think every one of you want to get a rough idea. So the fixed point 1, 2, 3 is actually corresponding to the non-flat case. And since you know that the universe now today is very close to the flatness, so we don't consider these 3 cases. And also these 3 cases, the fixed point that's corresponding to indeterminate equation state, and this value of the equation state. So it doesn't look realistic. So we remove 1, 2, 3 out. We don't really consider it. Fixed points 5, 4, 5, 6, 7, 8, 9 correspond to the flat cases. So this is our interest. But then we can think about a mathematical condition. Okay, if you think about universe start from if you omit a radiation era, we just begin everything with a stiff fluid. That means it's like a scalar field with very high kinetic energies. And these high kinetic energies will lose their energies by this friction term. So the effective equation state in the early universe will be like dust-like, effectively dust-like equation state. So if we consider that, it will be like the end of inflation. Okay, if we start with the end of inflation, and this will be corresponding to the fixed point 7 or 8. And then after that, let it evolve to the dust era, okay, which is a shadow point 5. And then finally, after dust era, let it evolve into the dark energy dominated era. And it's very cosmological constant like era at late time. So, okay, then we consider whatever condition in detail. There are physical condition that the kinetic term xc is a fixed point, right? X is a kinetic term, should be greater than 0. And if you have this greater than 0, it requires negative NMC coupling constant. Sorry, there's dogs barking outside, many dogs. And this require the NMC cannot be 0. That means it requires that you got to have NMC in this study. If you don't put this condition, that means the setting of the autonomous system from the beginning have to be changed. Okay, have to be changed from the beginning because this is a beginning of the derivation of the game. It's like a rules beginning, the agree rule of the game. So we have to work on this one. It's not 0, right? Except you want to approach GR case, you can take the limit when this value is going to 0. Okay, okay, and then for fixed point 5, as I've just mentioned, that you need, if you want fixed point 5 to be saddle point, that means the dust dominated era is actually a transient state of evolution. You can take the limit when C is going to 0 from the left side, from the negative side, to be physically valid. And that's great. Okay. And then the other dimensionless variable is S. S is a mixture between G effective. G effective, you know that there are NMC in here. It's like hidden bomb. And also you have explicit NMC here, hopping here. And then field, kinetic term, the speed of the field divided by the background expansion. So this one have to be negative. Why? Because you have now this one, right? You have now this one, negative. And then for expanding universe, H is greater than 0. For H is greater than 0, for the field to be positive speed. For me, I would like to say that I'm not gonna talking about this phantom scalar field or so on. When I talk about the field, I usually take the positive value, the speed of the field, take a speed value, because to me it look more physical. So that means S now have to be negative because C is negative, enforced by this condition. This condition force this, and then force this to be negative. Then with positive, this, and expansion, H is greater than 0. S have to be negative. And then if you take this small value approaching 0 from the left, the fixed point 7 is a shadow, and the fixed point 8 is unstable point. Okay, so okay, either 7 or 8 is both of these fixed points are stiff fluid dynamics. It can represent the end of inflationary era. So which one would be the beginnings point of our evolution? Right. So the problem for the fixed point 8 is that when you take this limit, fixed point 8 locate in S positive. And S positive for really, disagree with this one. This is negative. And fixed point 8 locate in 8 S negative positive. And that means fixed point 8 is not physical anymore because it's against this condition. Otherwise, you got to have negative Hubble constant, Hubble parameter, which is not really realistic. Okay. So the allowed region, the really fixed point at the beginning of our story, left only fixed point 7 as a shadow point. with the stiff fluid equation state. Ooh. Sorry about that. Okay, let's see this cartoon. So if you plot into this three dimension, A, Y, and S, okay, you can have the dynamical system phase portrait. Y is a potential term. S is easily mixed between the speed field. And as A is actually P square, okay? Just to remind you, let me go back to the slide. What is A? Okay, A is G fictive and phi square, also included all the coupling. Okay, S is this term. You have also the speed, and Y is a potential term. And now we use N is 2. Indeed, you can use the other three to plot because the independent dimension is 4. But then you can't really put 4 dimensions in here. You can put only 3 dimensions in the plot. So you can see these pictures. Okay, if you start from 7, you can come to 5, okay, and then come to 6 at the end. You can evolve from here to 6 and pass 5 here. 5 is a shadow point, okay? But then you can't see it very clearly. Let's see the cross section. You see the cross section, put Y here and S here. You can see the evolution from 7, stiff fluid at the end of inflation, then go to dust dominating era for temporary, and then go to the end, which is the dark energy dominated epoch. It's point 6, where the other sector on the right include the point 8, and this is not physical because S here is negative, a positive. So this S should be negative, it's false that. And if you plot A against S, it's the same. You will have something, you can start from here from 7, go to 5, and then go to 6. But 6 is not shown here because it's on the top view. On the top, you can see here. You can see only to 5. So the root is this. Okay. Okay, so if you follow this route, start from 7 to 5 and to 6, start from stiff fluid to dust and to dark energy dominated. We want to present you how much NMC effect can affect the dynamics. This is a plot of the Biot effective with the E falling number, and this is the past. This is the future. You can see that from stiff fluid, which is about 1 EOS, if you enhance the NMC coupling, you can see that the higher amplitude or magnitude of NMC coupling is in the black one, and the weak one is the blue, the strong one is the black. You can see this change. Okay, and then the pattern of the shape of this one, it doesn't really see the difference much. And then if you still have this one is large, okay, you can see this black line. But then from the constraint in the case of NMC case, and when C is 1, you should have at least very low value of NMC coupling. That means this should be go to minus 10 to the minus 7. Okay, so that means it could be something like this. That is a pure NMC case without holographic effect. So on the right side, if you fix this one to be something variable, why I don't use the value that constrained by the observation? Because you can't see even the plot. Yeah? I just want to present the anatomy of the plot. Because if you use that value, you just don't see the line, just out of the range. Okay. So if you fix this one to be minus 10 to the minus 5 or 1 in 100,000, and then you change the effect of the NMC, holographic effect. If you put C 0, that means no vacuum energy, it's gone completely. Okay. And if you put C is 1, that means the strongest one. You can have this green line for the strongest one. The weak one is this one. But this doesn't really cut. It just cut in the different value. Okay. And if you want to see the evolution, this is all the effect. When you fix, if you fix C constant and you change the coupling value, you can have this one. You can look at this slide in the future. I give it to the organizers. And you can see also in my paper last year, I give you the archive number in the front. And if you change the strength of the NMC coupling, you can have this one. Oh, sorry, change the strength of the holographic. Sorry, it's a bit small. You can enlarge it when you see the PDF. Okay, doesn't tell you much about what is what. Okay, let me conclude this. So this work is to study the non-minimal coupling effect with the Lipschitz scalar, with the quadratic potentials. So for purely NMC without holographic, the requirement is this one for the constraint, observational constraint from the cosmological perturbation. Okay. So in this paper, we consider the standard universe. That's an NMC field with holographic background energy using apparent horizon cutoff. And G effective is defined naturally at the Jordan frame Lagrangian level. Therefore, G effective to the universe is with this one, the universe is filled with canonical scalar field, thus an HD. Why I say canonical scalar field? Because the Lagrangian look canonical scalar field. Even though when you write down low phi or P, pressure P, you will have NMC emerged from in the term. But then when you talk about a theory, you should talk about the most fundamental beginning, which is the Lagrangian, not actually at the level of the equation of motion. All right. So therefore, since we define this one, so therefore the definition of the vacuum energy, we use G effective here, rather than just put G alone. We include the effective part of the NMC into the gravitational constant. So we use IR cutoff scale as apparent horizon because it's a trapped null surface similar to black hole interior. So this is natural choice. The trapped null surface just have to agree with the acceleration space-time. If you don't have accelerating space-time, so it's not trapped null surface. We use this potential. So we have 4 independent dimensionless parameters and 9 fixed points. So the effect appear in the G effective in all the dimensionless variables except for omega k and holographic effects that appear on this one only. That means the constant C doesn't appear somewhere else. And then you have trajectory rules in the flat case. Why we consider flat case? Because the point 1, 2, 3 corresponding to curved space case, and also give the fixed point that not really physical fixed point, because it gives you indeterminate and minus 1/3 value of the equation of state. Okay, so at the end we start from shadow steep fluid domination, resembling the end of the inflation, and then go to the shadow point of dust domination and to the stable case of the dark energy domination. And this looks similar to our universe. So the result, when you add the HDE result, that's not much different from the pure NMC case. So the HDE is only slightly change the situation. So it doesn't give you new anatomy or physiology of the dynamics, because this cutoff, this C is a constant, doesn't really evolve. Further suggestion for this study is that there should be someone confront this with the observational data. Right? Can't see the slide here because it's blocked with this backline. So how to do this? Okay. If someone can take this work and just collaborate with us, you can confront it with observational data. And another possibility is that right now we have the other type of entropy, which is non-additive entropy from quantum theory. So if we change how we define entropy from Hawking-Bekenstein entropy into maybe Salis entropy, and the other type like barrow entropy, this is going to change a lot. They're going to change a lot. And then because of if we change the value of entropy, so you have a new definition of the holographic dark energy. So if we give you a richer dynamical effect, the HDE can affect a lot on this dynamics. So that is challenging. All right. Thanks a lot. So that's 1 hour. And then that's the end of my talk. Thanks a lot for inviting me. Thank you.
Thank you, Burin, for the talk. Are there any questions? Yeah. There's one in the chat. Okay. Thank you very much for the talk. I think I missed a part of the talk. Given the non-minimal coupling, should HDE form be modified accordingly? Can it be cast into a distance measure in either Jordan frame or Einstein frame?
I don't hear, sorry. Can you do it slowly?
Oh, sorry. Thank you very much for the talk. I think I missed part of the talk. Given the non-minimal coupling, should HDE form be modified accordingly? Can it be cast into a distance measure in either Jordan frame or Einstein frame?
Right. Okay. Okay, with my limited of knowledge, right? Usually there's people working on both frames. So we can't really say that which frame is the correct one so far. As far as I understand, maybe I'm wrong, but then as far as I understand that some model are working on Einstein frame, some model are working on Jordan frame because it seems to be equivalent in modified gravity. So that's what I can say. I mean, maybe I'm wrong. You know, you can add. I think this need to have observational constraint on that. Actually, when we do it, we try to constrain it with this tensor to scalar ratio on the spectrum index of the inflationary universe. And also when you do have this spectral index, you can work with the perturbation, and that will rule out models. Yeah. But then there are some models still viable with the Einstein frame and then also viable in the Jordan frame, both. So we don't know which one is correct. Yeah.
Maybe we continue with Jutta, maybe.
Oh,
yeah. Thank you very much for the interesting talk. I've just been wondering about the choice of potential. Is it important? You only looked at phi square and phi 4. Is it important that you have the C2 symmetry in the potential? Or could you also have some odd terms? What would change?
Between n equal to 2 or n equal to 4.
And
right?
let's say, no, odd. So phi to the 3 or 5 or something like that.
All right. If you have a potential with phi to the 3 or phi to so on with odd number, you
Odd, yes.
usually come up with this ghost instability. And you can have you see, you have a potential that look like unbound from below, and then you have the difference between the potential term and the kinetic, the total energy into the negative kinetic. So you will come up with the very infinite negative energy. So we call gauge instability. So
Yeah,
that's why.
I agree. You would have this negative if you have a pure cubic or a higher polynomial. But if you take some polynomial, maybe the other terms might still dominate. So you might have a phi square, phi cube, phi 4 potential, and you wouldn't have that problem. But you might lose this symmetry.
Yeah, okay, maybe I don't really have that sort of knowledge you mentioned. I'm not particle physicist, but why I choose the simplest one, because it's simple and easy to work on. Yeah, and that's one of the reason, and seem that it look natural to come up from the string inspired theory, like 5 to the 4th or 5 to the 2, because some of this string in motivation from is actually the Ladon field or dilaton fields. So we try to look at the potential that have been used in the communities, because it have strong inspiration, and that's a point. But then maybe there's some other motivation that I don't know. So yeah, don't take my words. Yeah.
Thank you.
Thank you. Thanks so much.
Are there other questions? There's a follow-up question. Given both NMC field and standard field, wouldn't it be more natural that both contribute to HDE?
You mean we have NMC field, and the question is what?
So it's in the chat. Maybe if you can see it on your side, you can have a look at it too. I read it again. Given both NMC field and standard field, wouldn't it be more natural that both contribute to HDE?
You mean which one which is more natural to the HDE, right? How to get into the chat? I'm not really good at Zoom, sorry.
Could you maybe specify this point?
Okay, let me see the chat.
I mean,
okay, I saw it. Okay, I saw it.
okay.
Okay. Given both NMC field and standard field, wouldn't it be more natural that both contribute to HDE? Oh, okay. So you can see that in our model, we have an NMC term, and also we have the standard canonical term in there. So if you want to shut down the NMC part, you can just put C is 0, and then you will have a standard canonical field in the HDE, right? But then from the initial setting up of the equation, so if you set C is 0, so you have indeterminate equation, the denominator is 0, many terms, so you can't go further working, right? So I have to say I don't really know. We have to really confront that with observation. But then it's important when you set up the initial set of equation, if you put the condition that the coupling constant must not be 0, and that really tell you that you can't really work with 0 with no coupling at all. You got to have a coupling at the end all the time. Why we do that? We do that because from the work that I myself and Shinji Tsujikawa have done long ago. So actually it's his work, not really my work. You shouldn't take it's my work. He done a lot more than me. But the result is actually you have very tiny value of the NMC coupling constraint. That means it should be minus something 10 to the minus 7. And that's almost 0 anyway, but this is on the negative side for the model to be valid. Yeah, and it could be that those perturbation constraints are from this inflationary regime before it evolved into the HDE. So I don't know if this is natural. We just need to really do it with structure formation or whatever supernova confrontation. Actually, if it's there anyone who work on supernova data, you can take this equation of motion I give in the slide and you can just take it plot against the data. I'm not a data guy, so if someone want to work on this data analysis, I will be happy to work with really.
Are there other questions?
No, I mean both contribution different. Oh, right. Okay, contribute differently with different distance measure. Oh, okay. Sorry, just sorry. Yes. Yes. I think when you measure distance measuring from the supernova distance measuring angular distance, it should be there. But it should be in the background because it affects directly to the upper parameters. Yes. I agree. That will make a lot of difference. Yes. And that's why we need data. Yeah. And compare. You're right. Yes. You're quite right.
Any other questions?
This is the third time in my life I use Zoom.
So if there are no questions, I end the recording here.
Right. Thanks a lot.